Dear students, myself M. Kavita, Assistant Professor from Department of Mathematics. Today we discuss about optimization techniques. Before that, we have to understand what is optimization. Optimization is nothing but the art of obtaining best result under the given circumstances. On the other words, optimization is the process of getting optimal solutions under the given inputs. Rapid development and invention of new techniques occurred since the World War II, essentially because of the necessity to win the war with the limited resources available. In this presentation, we talk about linear programming problem. Linear programming problem deals with the optimization of a function of decision variables, which is known as objective function. Optimization means maximization or minimization, and then subject to a set of simultaneous linear equations or inequalities known as constraints. And the term linear means that all the variables occurring in the objective function and the constraints are of the first degree in the problems under consideration. And the term programming means the process of determining a particular course of action. Linear programming techniques are used in many industrial and economic problems. Linear programming techniques are used in many industrial and economic problems. They are applied in product mix, blending, diet, transportation, and assignment problems. We see some uses of LPP, which are airlines, railways, textile industries, chemical industries, steel industries, food processing industries, defense establishments. We see some requirements here. There must be a well-defined objective function, and second one is there must be alternative courses of action to choose. At least some of the resources must be in limited supply, which gives rise to constraints. Finally, both the objective function and constraints must be linear equations or inequalities. Now we see the mathematical formulation of LPP. If xj are the n decision variables of the problem and the system of m constraints, the general mathematical model can be written in the form optimize z equal to f of x1, x2, etc. up to xn, subject to the constraints gi of x1, x2, etc. up to xn, which is less than or equal to or greater than or equal to bi, and all the variables, that is x1, x2, etc. up to xn, all are greater than or equal to 0. Now we see the procedure for forming a LPP model. Here we have 4 steps. First one, identify the unknown decision variables to be determined and assign the symbols to them. And then identify all the restrictions or constraints in the problem and express them as linear equations or inequalities of decision variables. Then identify the objective or aim and represent it also as a linear function of decision variables. Finally, we express the complete formulation of LPP as a general mathematical model. Next, we see some remarks that are usage of manpower, time, raw materials, and etc. are always less than or equal to the availability of manpower, time, as well as raw materials, etc. Second one is production is always greater than or equal to the requirement so as to meet the demand. Now we see some problems. First one, a firm manufacturer 2 types of products, A and B, and sells them at a profit of rupees 2 on type A and rupees 3 on type B. Each product is processed on 2 machines, M1 and M2. Type A requires 1 minute of processing time on M1 and 2 minutes on M2. Type B requires 1 minute on M1 and 1 minute on M2. Machine M1 is available for not more than 6 hours 40 minutes, while machine M2 is available for 10 hours during any working day. Formulate the problem as ALPP so as to maximize the profit. Now we see the solution of the above slide problem. First of all, we assume the variables that are x1 and x2. x1 is number of units of product A and x2 is number of the units of product B. To produce these units of type A and B products, it requires x1 plus x2 processing minutes on M1, 2 x1 plus x2 processing minutes on M2. M1 is available for not more than 6 hours and 40 minutes. Now we convert this hour to minutes. We have 400 minutes. That is 6 hours and 40 minutes converted to 400 minutes. And machine B is available for 10 hours. Therefore 600 minutes. Therefore the constraints are x1 plus x2 less than or equal to 400, and then 2x1 plus x2 is which is less than or equal to 600. Then the variables are non-negativity constraint, that is x1 comma x2 greater than or equal to 0. The profit from type A is rupees 2 and the profit from type B is rupees 3, and then the total profit is 2x1 plus 3x2. Therefore the objective function is maximus z equal to 2x1 plus 3x2, and the subject to the constraints are x1 plus x2 is less than or equal to 400, 2x1 plus x2 less than or equal to 600, which are calculated in above slide, and the non-negativity constraints is x1 comma x2 greater than or equal to 0. Now we see the second problem. Old hens can be bought at rupees 2 each and young ones at rupees 5 each. The old hens lay 3 eggs per week and the young ones lay 5 eggs per week, each egg being worth 30 paise. A hen costs rupees 1 per week to feed. A person has only rupees 80 to spend for hens. How many of each kind should he buy to give a profit of more than rupees 6 per week? Assuming that he cannot house more than 20 hens, formulate this as a LPP. This is our second problem. Now we see the solution of the above problem. First of all, assume that x1 is the number of old hens and x2 is the number of young hens. He has only rupees 80 to spend for hens, and old hen cost is rupees 2 and young one cost is rupees 5 each. Therefore we have the constraint that is 2x1 plus 5x2 less than or equal to 80, and since he cannot house more than 20 hens, therefore the constraint becomes x1 plus x2 less than or equal to 20. The total sale of x equal to 3x1 plus 5x2 into 0.3, and the expenditure on feeding is rupees 1, and the total hens are x1 plus x2. Therefore we multiply that amount with x1 plus x2. The net profit is 0.5 x2 minus 0.1 x1. Therefore 0.5 x2 minus 0.1 x1 is greater than or equal to 6. The complete solution of the above problem is objective function is maximus z equal to 0.5 x2 minus 0.5 x1, and the subject to the constraints are 2x1 plus 5x2 which is less than or equal to 80, and x1 plus x2 less than or equal to 20, 0.5 x2 minus 0.1 x1 greater than or equal to 6, and then the non-negativity constraints is x1 comma x2 greater than or equal to 0. These points are remember in your mind. That is a well-defined objective function, and objective function and constraints must be linear equations or inequalities, and usage of manpower, time, raw materials are always less than or equal to the availability of manpower, time, and etc. Production is always greater than or equal to the requirement so as to meet the demand. Thank you.